Hello folks, this is Jeffrey Bale. My call sign is NT1K, and today we are going to measure the inductance of a wound toroid using the MiniVNA Pro. I went to a hamfest last year and I bought a bunch of these toroids, and a word of caution is when you're buying toroids at a hamfest, make sure you're buying the correct ones, because if they're not clearly marked or packaged what value and what type they are, you might not know what you're buying, because I've heard different manufacturers using different colors to mark their toroids. So I saw these, I got a handful, and they were like $1 or something, so I said, why not give it a shot? They're color red, so I'm hoping it's a type 2. I want to use these toroids as part of a high-pass filter I want to buy or build to get rid of some of the AM broadcast station interference I'm getting on one of my receivers. I have a couple AM stations that are really close to my house, and they do cause some problems, and since my receiver lacks filtering, this would quite help the situation. So part of the design of the circuit calls for a 4.1 microhenry inductor. So I'm figuring with these toroids I can do just that, create the inductor. With this little calculator I found online here, I typed in 4.1 microhenries of inductance, and it told me to use 27 turns of wire. So I did just that, and here is the final product here. I managed just to get enough windings around it. It's not my best winding job, but since I'm very new at this, I'm going to say not bad. I can get the spacing a little bit better and stuff like that. So problem is I don't have an LC meter. I do not have a way to measure the inductance. All I have is this MiniVNA Pro, so I figured maybe there's a way to measure the inductance using what this can measure. And I went to Google and I found 2 websites with 2 different ways of measuring the inductance, and we're going to try both of them today right here. So the first site I found was by a call sign HB9AMO. He has a website where he did some measurements of the VNA, and what we're going to do is put the inductor in series with a known capacitor, with a value of a known capacitor, and we're going to measure where the resonant frequency lies, and from there we can calculate the inductance. So let's start off with that one, with that method. And the first thing we're going to do is take the VNA and calibrate it. So with the adapters, I have a binding post adapter, binding post to BNC, and I have a BNC adapter to SMA. So I have a couple adapters, and what I would like to do is calibrate it and factor those out of the equation of the results. So what we're going to do now is get our software VNAJ here. We're going to go to calibration and hit create. If you do not know how to calibrate the unit, I have another video showing just that. So what we're going to do is leave these open, leave them attached, and we're going to read it open. And there we go. Next thing we're going to do is it says connect a 0 ohm load. So we're going to do just that. I got a piece of wire here. I'm going to jumper the binding post with. I know there's some resistance in it, but there's nothing I can really do about that. And we're going to hit read short. Third thing they want to do is connect a 50 ohm standard load to the binding post. I don't have a high precision 50 ohm load, so what I'm doing here is I got two resistors here, 100 ohm resistors in parallel. And the thing is I'm using resistors that are not really precision. They have a gold band on it, so that's telling me it's 5% tolerance. So our results are going to have a 5%. Our results are going to have a 5% tolerance, as well as the tolerancing of the capacitor used. So that proves to be not the most accurate way of measuring these capacitors, but at least we'll get inductors, but at least we get a general idea of what we're getting here. So let's read the load, and there we go. And we're going to save these results. I already did this, so we're going to overwrite the BNC load, and we're going to hit update. So what we're going to do now is hook up I'm going to have to do this off camera. We're going to take the inductor and put it in series with a known value capacitor. In this case, I have a 100 picofarad capacitor. And let's hook up and so the 100 picofarad capacitor I'm using is not precise. There's, I think, a 10% tolerance built into that, plus or minus, 10%. So it can't affect the results we get, but at least we get an idea if this is definitely the 4.1 microhenries. So here we have it. I have it in series. I got the toroid hooked up to the negative side. I got the other side of the toroid hooked up to a capacitor, and the other side of the capacitor hooked up to the positive terminal. I don't think it matters which way goes which. So we're going to lay that down here, and we are going to measure the phase, and we are going to measure that. So what we're going to do here is do a single pass. Oh, yeah, we're going to change our start and stop frequency. You don't want to go all 200 megahertz. So we're going to start off at 100 kilohertz, and we're going to go to about, we'll say 15 megahertz. So we'll type in 15M, hit enter, and we're going to do a single pass. And there we go. Right about at the 0 ohm point. And on the return phase, right where it goes 180 degrees or flips phase, that's our resonant frequency right there. So that's about 6.5 megahertz. Or 6.499, so we'll say 6.5 megahertz. So what we're going to do now is load the Excel file that HB9AMO has on his website that you can download, and we're going to go to inductor, and we're going to type in the known capacitor, which is 100 picofarad, and we're going to type in that frequency that it showed as a 6.5 megahertz. So let's type in 6.5, and we get a value of about 6 microhenries. That's far off from the 4.1 I calculated. So I'm not sure if that has to do with the toroid or the way I calibrated or the tolerancing of the resistors I used in calibration or the tolerancing of the capacitor. So we're going to also try the other method I found online and see if we get similar results to this 6.0 microhenries. So we're going to disconnect the capacitor, and we are going to hook the inductor directly up to the binding post, like so. I got to do this off camera because it's a little easier. So there we go. We're hooking it straight up. And the other method I found is by KP4MD. She has a nice website where she's done many tests, and I'm going to try her method. So let's X out of here. Nah, I'm not going to save it. Okay, so it's hooked up directly. We're going to do the same pass with a single, but this time we're going to export the data to an Excel worksheet. So you click the little Excel and it says it's been created and stuff like that. So what we're going to do is load the data, and here it is. And in row K, we're going to click line 3, and we're going to convert the frequency to megahertz. So we're going to copy and paste here. A3, which is cell A, row 3, equals times 0.00001. So that gives us 0.1 megahertz. So if we click that value and we scroll all the way down to the bottom and hold the shift key and then hit the last row there on 896, and then you're going to go to fill down, it will give you the calculations, and it ends around 15 megahertz. In row L, we're going to do the value I found on her, the equation I found on her website here. And we're going to type in the inductance right there. So here it is up here. You can find that. And there's the value. Let's just change the font, make it match the rest here. Arial 10. And then I'm going to click on that value, go all the way down, and hit fill down. And there we go. Next step you want to do is fill in these values. So we're just going to type in frequency in megahertz. If I can get my shift key. There we go, MHz. And we're going to go to value L and type in inductance. It's hard typing this way. There we go. So we're going to highlight column L, hit the control key, and hit column K, or wherever you have them. Going to insert, and we're going to do a scatter chart here with straight lines and markers. And then we're going to move this chart location to a new sheet. And there you go. You could see the plot here with the bottom being in megahertz from 0 to 16 megahertz. And on the side we got 0 to 7 microhenries. And you can see right around the 5.5 mark, you'll see it goes from 5.5 and it goes in roughly around 6 microhenries. I can go back to the Excel sheet here, and we can average out the inductance across the entire band if we wanted to, across the entire frequency. So if I go click in a column here and type in equals, average L3 to L896, or the last row, 896, close the bracket, hit enter. We have an average across the frequency span of 5.5 microhenries. So both methods came up with different results. I'm not sure which one would be closer. I would assume this one would be closer because there's no capacitor in series. So, but it's not the 4.1 I was hoping to get. So I'm not sure, once again, if that has something to do with the way I've tested the inductor, or if it has something to do with the actual toroid being used in the circuit. I'm not 100% sure if that is a true type 2 toroid. So, but it is giving me a 5.5 microhenry value, or 6.0. So I just wanted to show both methods to calculate the inductance. You can also use these methods to calculate the capacitance of a circuit as well, using the MiniVNA. So hope you guys found this useful, and if I did something wrong, please correct me, because I'm still learning this, and I figured to share how I'm learning and what I'm learning. If you like these videos, please like and subscribe. It knows that you guys are actually watching these, and that maybe I should make more. I'm not sure. So once again, thank you for watching, and enjoy. Thank you very much.